Hey, hello. So in this video, I'm going to go over the problem A5 from 2019, Putnam 2019, which asks us to find the largest power of x minus 1 that divides a polynomial. So it gives you a p that is an odd prime, and fp is the field of integers mod p, and fp of x is the ring of polynomials. We take a polynomial that is given by some formula. So essentially all of the AKs are k to the power of p minus 1 over 2. So since you are working inside fp, you could just ignore mod p. And we are trying to find the greatest non-negative integer that x minus 1 to the power of n divides q of x. Okay, so the first thing I'm going to think about is, what does it mean to find the largest power of x minus 1 dividing a polynomial? So if I have a polynomial q of x, and that is x minus 1 to the power of n times another polynomial, let's call that f of x, how am I going to be able to find that power of n? Of course, one way would be to factor the polynomial q of x and factor it again, and again until you get to something that f of 1 is not 0. So that's, of course, one way of doing that. But it doesn't look like in this problem we could actually evaluate, like factor the polynomial that I'm given. It's a very complicated polynomial, and it's not quite clear to me how I can factor that. But I could think about other ways of finding the largest power of n that x minus 1 to the power of n divides a polynomial. One way of thinking about that, if you have a polynomial q of x, and it can be written as x minus 1 times f of x, essentially the only thing you need to check is that q of 1 is equal to 0. If q of 1 is equal to 0, then you can factor x minus 1 from q of x. If q of x has two factors of x minus 1, then what you can do is q of 1 is equal to 0. But also when you differentiate, you get another root of 0. That's not very difficult to see, because if you differentiate q, then you get 2 times x minus 1 f of x. And this is the formal differentiation. So it's not like, because we're working mod p, it is just formal differentiation of polynomials. Plus x minus 1 squared times f prime of x. It doesn't make sense to define it as limit, the limit definition for derivative. And of course, that means q prime of 1 is equal to 0. So that's interesting, because if I want to find out what is the multiplicity of 1 inside that, that's essentially what I'm asked to do. Essentially, the question is, what is the multiplicity of 1 as a root of q of x? So that's the question. That's what they're asking me to do. So what I know is that if I want to find the multiplicity, I have to find q of 1. I have to find q prime of 1. And if I can find all the way to q n minus first derivative at 1, if these are 0 and the next one is non-zero, q n of 1 is non-zero. If I can find an n that satisfies this, then I know that x minus 1 to the power of n divides q of x, but the next one doesn't divide it. Okay, so the bottom line is I'm trying to find powers, derivatives of q and at 1. So I have to find derivatives of q at 1. So q of x was given as the sum k to the power of p minus 1 over 2 x to the power of k, I believe. And k ranges from 1 to p minus 1. So first thing is plug in 1 and see what we get. So plug in 1, we get q of 1 is equal to the sum k to the power of p minus 1 over 2, k equals 1 to p minus 1. Okay, so that's interesting. So the question is asking me to find powers of integers 1 to the power of p minus 1 over 2. So the question is essentially at this point, it's 1 to the power of p minus 1 over 2, 2 to the power of p minus 1 over 2, 3 to the power of p minus 1 over 2, and so on, all the way to p minus 1 to the power of p minus 1 over 2. So I'm trying to figure out what is this sum. And of course, in FP, mod P, what is that sum? Well, this is a fairly well-known question to find the sum of powers of consecutive integers mod a prime. But if you aren't familiar with how to evaluate that, I'm going to tell you how this can be evaluated. So it is really inconvenient that we are working with an arithmetic sequence, but we are raising it to powers. So that makes it difficult to compute. It makes it difficult to compute this sum. Instead, if I had a geometric sum, raising it to a power is very nice because it makes it still another geometric sum, and geometric sums, you have a formula for that. Okay, so now, is there any way we could relate arithmetic and geometric mod P? That is my question at this point. Because I know that if I have geometric, I raise to the power of P minus 1 over 2, I can evaluate those sums. This reminds me of a concept in number theory called primitive root. So this is a theorem, which I'll write it down just in case you're not familiar with. But it's a very well-known theorem. You don't need to even state that in the exam, in the Putnam. You could just mention primitive root. So here's what it says. Let P be a prime. Then there is some G between P minus 1 and P such that G to the power of, I guess G to the power of 0, G to the power of 1, G squared, all the way to G to the power of P minus 2 gives us all non-zero remainders mod P. So it gives us all of the non-zero remainders mod P. Okay, so what does that mean? It means I can take these and instead of having, so in other words, 1 to the power of P minus 1 over 2 all the way to P minus 1 to the power of P minus 1 over 2. That is just going to be, one of them is G to the power of 0. One of them is G to the power of 1. One of them is G to the power of 2, and so on. So it is just the same thing as G to the power of K. K equals 0 to P minus 2, and then raise that to the power of P minus 1 over 2. Because these terms and the terms 1, 2, 3 to P minus 1, those are the same thing. Okay, and this is also mod P. Everything is in FP. So that's nice. I can now evaluate that because I have a formula. I have an explicit formula for that. It is a geometric sum. So geometric sum is first term, which is 1, minus the term after last, which is G to the power of P minus 1 to the power of P minus 1 over 2, divided by 1 minus common ratio, which is clearly 0. So because g to the power of p minus 1 is 1 mod p. And just notice that the denominator is not 0 because g is a primitive root, so this is not 1. G is a primitive root, so g to the power of p minus 1 over 2 is not 1 because there is no repetition in the list of g to the power of 0 all the way to g to the power of p minus 2. Okay, so we successfully showed that g of 1 is in fact 0. But that's just like one step. So I have to look at g prime of q prime of 1. So q prime of x is, I have to take the derivative. So it was k equals 1 to p minus 1, k to the power of p minus 1 over 2. The polynomial was x to the power of k. So differentiating that, you get this. And that means q prime of 1 would be the sum k to the power of p plus 1 over 2. K equals 1 to p minus 1. And I have to evaluate that mod p. So in fp, that is the sum g to the power of k to the power of p plus 1 over 2. K equals 0 to p minus 2. So we're doing this essentially the same thing. Geometric sum, first term, minus term after last, divided by 1 minus common ratio. Again, that's 0 over 1 minus g to the power of p plus 1 over 2. So denominator is not 0 if p plus 1 over 2 is less than p minus 1. So you can check that when that happens. So you see what's going on here. Now you can take the derivative again. If you take the derivative again, you'll get g of x, g double prime of x. So that ends up being 0 in that case. And that's just like, it eliminates, I guess, one possibility. So this gives you p is more than 3, I believe. So it eliminates the possibility of p equals 3, which is okay. So eventually the final answer would depend on what p is. If you take the derivative again, you get the sum k to the power of p plus 1 over 2 times k minus 1 times x to the power of times k minus 1 times x to the power of k minus 2, k equals 1 to p minus 1. But that is, if you plug in 1, you get g double prime of 1 equals the sum. There are two different sums. You could write it down as k to the power of p plus 3 over 2 minus k to the power of p plus 1 over 2. K equals 1 to p minus 1. Both of these two, you can find what they are with the exact same process. So we seem to be in the right track. So if you just repeat that, all you need to do is to figure out when the denominator becomes 0. If it is 0, then you have to stop. I'm going to write down the solution now. I have done this before and figured out what the number should be. So I'll write down the solution now. So now that we figured out what we need to do in order to solve the problem, we'll just put that together and write down the solution. Okay. So the first thing I do for a solution, I'm going to write down exactly what the answer is because I want to like have it up there clear, so that it's clear that actually I have gotten the correct answer. So here's what I'm going to do. So the answer is p minus 1 over 2. So then we're going to go ahead and prove that. So we need to prove if n is between 0 and p minus 1 over 2, then qn of 1 is equal to 0. And so we need to show all of the derivatives up to that point, it is 0. and p minus 1 over 2, if you take the derivative p minus 1 over 2 derivative, you get that's not 0. So if I show this is the case, then I'm done. So we'll go ahead and evaluate the derivatives and show exactly that. So q of x is just the sum k to the power of p minus 1 over 2 x to the power of k. We'll take the derivative. We get q prime of x is equal to the sum k equals 1 to p minus 1, 1 to p minus 1. If you see really what happens, I would just write it down. So it's just q to the power of k to the power of p minus 1 over 2, then k minus 1, all the way to k minus n plus 1. Yeah. And this is the nth derivative. So the first derivative would go up to just k. Second derivative would be k times k minus 1 times x to the power of k minus n. I have that. And that means the nth derivative of q at 1 is the sum k to the power of p minus 1 over 2, k minus 1, all the way to k minus n plus 1, k equals 1 to p minus 1. Now we're going to repeat the same thing that we did before, which is just saying that this is a linear combination of these things. So the sum of k to the power of p minus 1 over 2 plus 1, and then the same thing, k to the power of p minus 1 over 2 plus 2. So either you choose only k or you choose 2 of those, and so on. And in fact, the very first one could be also plus 0 if you don't take any derivative. So it is just taking a linear combination of these all the way up to, I do need to write down the very last one. So the very last one is going to be the sum k to the power of p minus 1 over 2 plus, so since I have taken n derivatives, it would be plus n. And this is all k equals 1 to p minus 1. So, okay. So this is the case where n is less than p minus 1 over 2. So suppose n is less than p minus 1 over 2 and at this 0. So note that this p minus 1 over 2 plus n is going to be less than p minus 1, and of course more than 0. So the sum, so if m is between p minus 1 and 0, then the sum of k to the power of m, k equals, okay, I guess at this point I'll have to mention that g is a primitive root. So let g be a primitive root mod p. So I'm taking the primitive root mod p, which is what allows me to evaluate this sum. K equals 1 to p minus 1. That's equal to the sum g to the power of k to the power of m, k equals 0 to p minus 2, which is equal to 1 minus g to the power of p minus 1 to the power of m over 1 minus g to the power of m, which is 0, since g to the power of m is not 1. And this is because m is less than p minus 1. So we have that. Therefore, all of those terms are 0. So Gn of 1 is in fact 0 if n is less than p minus 1 over 2 and greater than or equal to 0. If n is equal to p minus 1 over 2, then the sum of k to the power of p minus 1 over 2 plus n is the sum of k to the power of p minus 1. K equals 1 to p minus 1. But k to the power of p minus 1 by Fermat's little theorem is just 1. So that's just going to be a sum of a bunch of 1s. K equals 1 to p minus 1, which is just p minus 1, which is in fact just negative 1, since we are in FP. We are working in field with only p elements, so p is just 0. So thus, the very last term, the Gn of 1, is in fact non-zero. That's non-zero. And this means this completes the solution for this problem. So again, there are 2 points in this solution. The first one is, what does it mean to find the largest power of x minus 1 dividing a polynomial? It means you're trying to find with the multiplicity of that root, which means you have to plug in that root of 1 into the function, into the polynomial, and into its derivatives until you get something that is non-zero. And the second thing is, how do we evaluate these sums? There are other ways of evaluating these sums, and I encourage you to think about how to evaluate these sums. This is something I want to mention. So I'm done with the solution to this, but I want to mention that these sums can be evaluated in other ways, and you would be able to come up with other solutions. So if you want to evaluate 1 squared plus 2 squared plus 3 squared all the way to n squared, you can follow this process. So just start with x plus 1 cubed, which is x cubed plus 3x squared plus 3x plus 1, and plug in different values. So you have 1 plus 1 cubed is 1 cubed plus 3 times 1 squared, 3 times 1 plus 1. 1 plus 2 cubed is 2 cubed plus 3 times 2 squared, 3 times 2 plus 1, and so on. And then 1 plus n cubed would be n cubed plus 3n squared plus 3n plus 1. When you sum these up, these terms are going to cancel from the two sides of the equality. And what you get is 1 plus n cubed equals, you have a 1 cubed here, 3 times the sum of the terms squared, then 3 times the sum of the consecutive numbers. And then the last one would be, there are n ones that we're adding. You can solve for this guy. You cannot come up with a formula for 1 to the power of k all the way to n to the power of k. That's not going to be easy, or not really possible. But you can come up with some recursive formula. And I believe that should be also enough for you to solve this problem. If you weren't familiar with primitive roots, this is a good place to learn about them. But just have that in mind, that this is also a good technique to evaluate the sum of powers of consecutive integers. And this technique could also be used to solve this problem.